Next speaker is Dongqing WEI from Shanghai Jiaotong University. Let's welcome.
Okay, I would like to thank John and friend here at the Normal University, which is our neighbor in the Minhang campus. So my talk is about the rare event dynamics and ion transportation through protein channels and also across membranes. CADD stands for computer-aided drug design. So we could also get some information on the CADD by studying the structure and dynamic process of the membrane proteins. So those are the a few examples of membrane proteins. So you can see the cross-membrane part are mainly arc helices. You have beta sheet, and they are well structured. The best known are the potassium channel and also nicotine receptor. We are interested in the exchange of material information, especially informations, and signal transduction. And also gating mechanism and free energy calculation, rational drug design. So since 1985, we have about close to 500 structures of proteins. It also goes like exponential, which is similar to the curve for the genes, the new genes in the data bank. But very few structure for the membrane proteins, which is very hard to be crystallized. But you see, this is the main technique for obtaining protein structures. And that requires crystallization of a protein. MR, you can get small proteins. You see the size of the system increase, and also the time. But you see the simulation technology now is quite powerful tool now, studying the protein structure, including membrane proteins. And also, this is really average, one snapshot of the protein structure, MR and X-ray, but we do have a lot of copy or sampling of these protein structures. So it's a very useful tool now. So I'll give you an example of our study of the membrane proteins. So the first one is nicotine receptor. And this is the structure. This is the cross-membrane part, and this is the extracellular part of the protein. And it's really like a dimer of a beta sheet protein. And this is the binding site where it controls the gating of this protein. And the ligand is a small molecule. Nicotine molecule is an example. It could regulate the process of these particular proteins. Sorry. The second example is this M2 ion channel of influenza A. It's well studied. There's a lot of paper on this system. It's initiated in 2008. There are two publications on Nature. One by James Cho. I'm sure some of you heard of him. He's from Harvard University. And, he's now also have a joint appointment in Shanghai. And another is from the Philadelphia group. It's a small protein with only 4 arm helix. And this type of system can be studied by NMR. Anything larger will be very hard. It's a proton channel, which is very rare. And you see, the problem is how the proton transport through the channel, and how this a small molecule will regulate. For example, this one will regulate the process, to create a barrier, or we call it gating, to the proton transfer. So you can see there are a lot of recent works on these proteins. And you can see the structure. If you look at the pore of this, there is a hole inside. And if you look at the difference between various structures, they are very different. This is the hole, the pore size, pore distribution, if you like, by James Cho, the Harvard group. And this is the pore distribution of the Philadelphia group. And yeah, I believe it's this one, where the molecule is bound inside the pore. So you expand the pore size significantly. You can see. And this one, I'm sorry. And there are other studies. So the key to this problem is where the small particle would band, inside the pore or on the side. From the Harvard group, they believe the molecule should band on the side symmetrically. There's 4 molecule banding. And indeed, it's create a very big barrier for the proton to be transferred through the channels. So we did a molecular dynamics simulation for this M2 proteins. Very standard technique using Gromov force field and also umbrella sampling, because if it's regular dynamics, it takes a long time to converge. And also there's an important mutation which believe to be important for the drug resistance of this, well, it's an old drug. So it should be understood how it affects on the pore distribution. And so this is the apple, empty. The protein is empty without molecular binding. You see this curve. And this is P binding, P is binding inside. So the size of the channel increase. And this is what we call S binding, where it's bound on the bottom of the protein. So if you, so this is the P binding, where the molecule is inside of the pore. The S binding bound on this side, the bottom of this arm helix. We did calculation using 2 force fields, GROMAX and OPLS, and the result is quite similar. We did the free energy calculation to see which binding is favorable in this situation, because there's a lot of debate on where the molecule bands on this M2 channel. So we construct these few passes where the molecule, which is hydrophilic, goes from the solvent to this binding side and to this barrier. This is the membrane, and also to this binding side. So you can see the free energy profile goes to this is the membrane. This is the binding side inside the pore. inside the protein. And this is the potential beam force across the membrane without the protein, without the presence of the protein. And this is the potential beam force where the molecule goes across, the same story here, but different force field. And this one goes from the solvent to cross the membrane to the S binding site. So the story is summarized here. So this is the molecule. It's a very small molecule with a ring, and this is the free energy goes to inside, and this is the barrier. This is the binding free energy. This is the barrier. So to go to inside the protein has to across a barrier of 10, and if it goes from the solvent to this binding site, doesn't cost anything. But the binding free energy is smaller. Instead of 20, so this is about 11. So what we want to say is this site is like easily accessible, but the binding is less strong. This one is a very strong binding site, but it has to cross a barrier. So this is what we probably a dynamic or kinetic binding site. This is a small dynamic binding site. So they are all possible. And also you can see there's also two sites, beneath the membrane. It doesn't cost much energy from here to here. So by doing this kind of calculation, we can clarify some, hot debating problems in the experiment. So the next example is nicotine receptor. It's a well-known target for this Alzheimer's disease. For human, is what we usually refer to as alpha-7 receptor. So this is the structure of the receptor, the protein, membrane protein. As I mentioned, this is the binding site. This is 5 membrane proteins with, of course, a channel, a hole inside. If it's alpha-7, they are all the same, all alpha. There's many class of these proteins. But for human, they are all the same. It's dominant. This alpha-7 is most dominant for human. So we want to understand through studying the ligand binding with this receptor, alpha-7 receptor. So many years ago, we have some very simple work, some quantum study on these molecules, which is a new candidate for this Alzheimer's disease. I think in the 3rd phase of clinical trial. You see it's quite different from nicotine. Nicotine had only one ring, and we believe this class of molecule would be very promising. It has a positive charged nitrogen and some hydrophobic part of a molecule, and also there's some polar portion in these molecules. So we could use this as a template to screen the database. It's a well-known technique in the computer-aided drug design. So it's like we use this template and also use this only dimer, because we only want to interest on the ligand binding part of the protein. So we use the similarity search first, and this Lipinski rule 5 is well known in this drug screening field. So we also do, typical Dongqing and also MD, because Dongqing is rigid. So we want to. There's no good flexible Dongqing programs. So you have to sort of visually examine after this result. Eventually, we want to get a drug candidate. Hopefully, it's an agonist. So it's a molecule can regulate the gating of this protein. So we start with 10,000. That is what you have for this traditional Chinese medicine database. It contains molecule extracted from Chinese traditional medicine, these herb medicines. Right now, I think you can have about 15,000. When we studied when we did this work, it was about 10,000. So include more molecule from when you apply more rules. After Dongqing, you get 40 something. And MD, well, MD is still expensive. And so eventually we get 7 molecules from this screening. The best candidate is this molecule. You see, it's quite similar to the template, to the molecule, to the target molecule we used to screen the database. It actually it's from Sichuan pepper. Actually, it's very high concentration. It's about 1% of this ingredient from this Sichuan pepper. We can do molecular engineering. We can modify the molecule and do the same Dongqing, same MD, and try to see which molecule get a class of molecule that promising for as a drug candidate. So you can do experiment, and the simplest experiment is this macrophage experiment. LPS will induce the release of inflammatory factors. These 3 inflammatory factors. It's well known. For example, nicotine would inhibit the release of these factors, so that it can be used as anti-inflammatory agents. So any ligand of this alpha-7 would, if it's a good one, it can be used to inhibit the release of these inflammatory factors. So this is the molecule we call it GXW50, WGX50. So that will reduce the release of inflammatory factor. So you can see this well exhibited sort of concentration dependence. It shows it's effective. And actually, the concentration is very low in nanomole. It's effective. So most of the molecules extracted from Chinese traditional medicine, they are not strong enough. They need high concentration to inhibit to be useful, to be effective. And also, we have to pre-treat the macrophage with the existing inhibitor of the alpha-7. You can see the effect is reduced by adding this new molecule. So it means it's possible this thing functions through the alpha-7 receptor. And also, it doesn't have much toxicity, this molecule, because it's natural, it's expected from the cell viability study. So the conclusion is that this molecule could inhibit release of inflammatory factor induced by LPS, and the action is made through this alpha-7 receptor. So it is possible this molecule could be a good candidate for this Alzheimer's disease. So we did more experiments. We know for older patients of Alzheimer's disease, there's accumulation of this polymer called a beta aminoid. It's a peptide composed of beta sheet, and there's a lot of accumulation of this beta aminoids. But by applying this molecule directly excellular, you see it being dissolved. But this thing has nothing to do with the alpha-7 receptor. So we say this disease has multi-targets. This is just a typical example of such multi-target story. And also, we inject this molecule to mice, and it also shows disappearance of this accumulation of the beta aminoids. And also we did animal experiment. This water maze experiment is well known as an animal model of this Alzheimer's disease. And we inject some poison molecule to the mice, and so that it lost memory immediately. So this molecule would be able to recover its memory, very effectively. And also we tested on the genetic modified mice. You see, this is the genetic modified, positively modified mice. The memory is recovered after certain period of application of these molecules. So what I want to demonstrate is this simple calculation used MD could be useful in this drug discovery process. And also what is more, we did, because there's in the skin, there's a lot of alpha-7. So if it works for the brain, it sure works for the skin. And we know ladies from Sichuan has better skin. You see? Well, I don't know how to translate. It says people from Sichuan has more beautiful girls. The face, it looks like flower. The skin. So what we did is very simple. We have like very old mice, 20 months. And on one side, we only apply some kind of solvent. And by the way, this molecule doesn't dissolve on water. So if you want to benefit from this molecule, you have to, dissolve it, use the oil, extract from the oil. For example, the Sichuan hot pot, would have a lot of, molecule inside. Water doesn't work. And on the other side, you put this. You see the comparison is very obvious. You see the skin is heavily damaged because it's like 80-year-old lady or man, right? A lot of holes, and also you don't have hair, no hair anymore. The hair actually grows back, you see, because, and also you see, it's filled up the skin. So we are applying some patent, for the skin product.
Mouse skin or human skin?
Mouse. From the human, you can't do experiment. It's illegal. So we have to apply for permission. Okay. My student tried, with his hair. He's only 20-some years old. It doesn't work for him. Probably you need to have a certain age. Okay. So anyway, so theoretical chemistry is useful. So the last part of my talk is on this no protein at all. How the ion permeate through the membrane. This is a well-known problem where you see the ion concentration are different across the membrane, which is needed for us. If we don't have this, we would die not long. So we want to understand the mechanism across this membrane. There's some study, but there's problem. The previous study calculate the potential moving force, for example, only from one side. And you see it's not symmetric, which is wrong. Because this membrane, they are symmetric. What we call hysteresis. And it's seriously dependent on system size. And the free energy calculation relies on this array event dynamics. A typical technique is called umbrella sampling. So I have this family tradition. This is the father of umbrella sampling from University of Toronto, Jiaotong WEI. In 1970-something, he developed this technique. This is my boss, postdoc fellow, boss at UBC, Grand Prix, and so I'm taking over. Hopefully I can develop some new technology in the umbrella sampling area. And this is my student. He did the job. Okay. So you see, the problem is really the ion has hard time to cross it. And when it reaches to a certain distance, not only this side, the membrane, is different from the equilibrium state. That is, the ion is here. And the other side has to respond. That is the problem with the old technique. You have to include molecule from this side in order to get credible result. You see, that's why, it keeps increasing. It should go down, when you cross the membrane. And also, the problem is also, when molecule reach the center, it's very hard to get any sampling. Means the event is really rare. So it's almost impossible to cross the membrane. So we have to reconsider the reaction coordinate, because we know in the sampling, especially umbrella sampling, reaction coordinate is very important. So you have to define, actually it's very complicated. A reaction coordinate involves the other side of the protein, water, and also solvent. And so, water inside the membrane, you will see. It's different from the water as a solvent. So indeed, with the new reaction coordinate, we see, starting from a zero conformation from the equilibrium state, start to cross the membrane and reach, look at this, reach the middle point. We see that with help of water pore, water chain, if you like. And it goes to the other side. You see a whole picture of the ion across the membrane for the first time. It has been never achieved. So without this coordinate, the sampling, for example, at this state, is almost impossible. There's no sampling. So we can see how many, time it reaches the middle point. You get samplings. And also, we get good result, almost symmetric, you see, with large size. And also, the results depend on the system, on the size of how many membrane you use. And we avoid the hysteresis because there's no sampling here. That's why you get a lot of hysteresis. And this is a real simulation. You can see there's still not many sampling here. Not sampling here. And we did an experiment. We started IMD simulation without rare event, a regular molecular dynamics simulation from the saddle point, and let it go, and see how the system found its way back to the equilibrium non-transformed state. You see, it doesn't go here. It goes here. So it found an even lower free energy path. So that let us realize, probably you need another reaction coordinate to describe this phenomenon. It doesn't go here, it goes here. Because this is rare event that we force them to cross the membrane. It's not natural. So that let us believe. You see, if you see the free energy path, it's in fact found the best path. If we plot two-dimensional, and the other coordinate is actually the water chin coordinate. I can't describe how I define this. It's very complicated. But in order to see this low free energy path, you have to have used another coordinate helped by water. In fact, water chain. Without the water chain, the ion, positive charge ion, can never cross the membrane. Even with this help of water, it's pretty hard. It requires 20-some kilocalorie free energy to cross the membrane. So this is the story. You need a new coordinate, reaction coordinate. Besides, the thing I defined involves both sides of the membrane in order to find the minimum free energy path. So I don't want to explain too much. So and recently, we want to study how the peptide across the membrane without any, just brute force MD simulation, without any umbrella sampling or rare event. You see, if it's long enough, we see, it's really crossed the membrane. And more amazingly, we found for longer peptide. For long peptide, we see self-assembly into a protein channel. So hopefully next time I will show you the result of self-assembly and brute force MD simulation. Thank you.
Questions?
We're trying to use a template to screen the compound from the TCM library of 10,000. So you use this called shape matching stuff?
Oh, I use similar research. So what I do is I fingerprint the molecule. Fingerprint. There's many ways to fingerprint the molecule.
So what is the sample molecule? So the reference molecule that you use to screen?
So that is the molecule we prove is a drug.
Non-drug, right?
Yeah, non-drug. Yes, that's a template.
The similarity is based on the shape, basically.
Oh no, shape is one of them. For example, you can use the pharmacophore
Okay.
or other things, or polarizability or
This is kind of method you develop yourself, or it's kind of
we have a tool like this, and it's also available commercially. All the commercial
It's your own
tools.
program.
Yes,
It's your own program.
our own program we use for this screen.
It's available.
Yeah.
It's commercial.
Commercial, no, we don't sell it, but many commercial package would have this molecular screening. For Schrödinger or Hysteresis or MOE, they all have this screening. So they can screen to a million molecule, for example, one day, or more, even more.
More questions? So, I have one question. So, what's the integration mechanism for the GX50 on the aggregation of adenine and
Oh, okay. Okay, that's a good question. Professor Wei is also doing membrane protein simulation. So we are. So for that, the mechanism is not clear, but there are already few molecules could dissolve the beta aminoids. So we are one of my students doing simulation, MD simulation, how we dissolve it. Well, you know, I haven't seen any good results so far.
Thank you. So if no more questions, we thank Dr. Professor Wei.
Well, it comes to the end of this workshop, and I would like to thank all the speakers and all the session chairs, and in particular all the audiences and the students who come to this workshop. That really is critical to make this workshop successful. So this is the. No? So this is the first workshop organized by the Center for Computational Chemistry at NYU Shanghai, and I'm really thankful for all the people who come here and to support this workshop. And this gives us really an encouragement to perhaps do a better job, maybe next year and in the future definitely, and probably even a larger scale. And if anybody have any suggestion, I think we have maybe 10 minutes, so we can just stand up and tell us what we can do to improve the conferences or symposium we plan in the future. Anybody would like to give us any suggestions? So, Professor Shuai, you are the Shuai means the chief of general.
Okay. ICQC satellite, Shanghai.
So, any member of our centers would like to say something? So Zlatko, you
Well,
you always have a lot of suggestions.
for organizing, doing the lion's share of the organization of the meeting. So, John.
Thank you.
Second, I told you that already.
Take the microphone.
I think it would be nice to have more time for discussion. Actually, I know that it's the time for the conference or decreases maybe the number of speakers, but I think that adding time for informal discussions and questions and so on is very important. It makes the whole thing more meaningful. So that's my main suggestion. Otherwise, excellent.
Well, thank you for thanking me, but I should really thank the people who are really behind all these organizations. And for example, this young guy, Jingbo, and although he's young, he's done so much work. For example, the website of the conference, all set up by himself. And we have Lily's, and she's probably not in today, and Yayue, who is sending emails to everybody, is organizing logistics, and of course also Angie Chen, she's really my boss. You know, she's providing all the needed support, including monies, which is the most important factors to make this workshop successful. If we don't have any other events, anybody want to say something, I would like to conclude the workshop, and I would thank everyone and again, and I wish you well. And I'm sorry it took over 2 days, all weekends, so you don't have time to enjoy your weekend. And spend a complete 2 days sitting in the audiences. This is very hard work. But I would like to say, especially for international guests, this is becoming quite common to have these symposiums and workshops on weekends, because this is the only time most people can come. If it's weekdays, all the guests from Beijing, they cannot come.
It doesn't matter to us. It's just terrible jet lag no matter what.
Yeah. Well, it's if you come here more often, I think the effect of jet lag will reduce exponentially.
I'll be so confused it won't matter, right?
Okay, so I would like to conclude the end of this workshop, and thank you for attending this workshop. Okay.